Alright, today we're going to be doing problem number 5 of homework number 9. The problem reads as follows. Suppose we have a function y in terms of t, some sort of variable, which is basically defined as the integral from negative infinity to positive infinity of this function x, which is going to be written in terms of some random t minus a tau variable, which is another time variable, and the times this other function, which is going to be written as h in terms of tau, and the integral is going to happen over tau, not in terms of t, but in terms of tau. That's how we define our y. Now, the other thing we have to define is this h in terms of tau, which is basically h of t, it's some time function. It's an arbitrary deterministic time function right here, okay? And basically our x right here is going to be written as some Whitehead stationary stochastic process, okay? The properties that we have, because it's Whitehead stationary stochastic, is that its expected value of our process x in terms of t is going to be equal to 0. The other thing that we're given is that our autocorrelation terms in terms of x is going to be defined by the Dirac function, the delta function of t1 minus t2. Alright? So that's how we define these things. And the question is basically asking us, again, find the expected value in terms of the y function, alright, and also find the expected value in terms of the square of the y function. Alright? So the problem's actually halfway straightforward. So let's start by figuring out this term right here. So expected value of the y process right here is, we're going to substitute in our equation for y, which we do right here. So expected times overall the integral from negative infinity to positive infinity of x in terms of t minus, and we define, instead of saying tau, we define some random unknown tau. Tau's too much like definitive. We're going to use alpha as a substitute term for tau. Okay? So we actually put this t minus alpha. Again, right here we use the actual deterministic time function, h, in terms of alpha, and the whole thing is going to be integrated over alpha. Okay? That all we did was just substitute this in here. And as we can see, if we actually break this down, alright, we can actually we can actually flip these two terms, the integration term, we can bring the e on the inside, so we can actually figure out this is going to be the expected value, this term right here, times our deterministic function h at alpha, all over d alpha. I mean, we just rearranged some terms at this point. The thing is, this term right here, what do we know about this term? This term right here is basically this term, okay? It's just where, I mean, here we define it as some random t. This is t minus any sort of constant. What we know is that at any time point, the expected value is going to be equal to 0. So this value is going to also be equal to 0. So if this is equal to 0, or basically this whole product right here is equal to 0, the integration from negative infinity to positive infinity is going to be equal to 0. So our final answer for the expected value of our y function is 0. Now, if we proceed forward to look at the answer for our expected value in terms of the square of this y function, alright, again, we substitute in, but this time what we're doing is we have to find the product of this y times itself. What we're going to do, like here, we're going to use a substitute for tau. We're going to call it alpha for one of the y terms times the same term, but we're going to use beta over here. So basically, we're going to multiply this term times itself. We're just going to use two different terms to signify different taus. So again, we bring this term down, integral negative infinity, positive infinity, x t minus some alpha times the deterministic function h, all in terms of delta alpha, times pretty much the same thing, same type of integral, x t minus beta deterministic function in terms of b over delta b, over db. What we can do here is basically, and then basically rearrange terms. So what we can do is that we can actually make this a double integral. So we bring this over here, rearrange these two so they're right next to each other. The two x terms are right next to each other. We can rearrange things so the h functions are right next to each other, and we can rearrange things so the d functions are right next to each other, which is what we do right here. So we got a double integral, the two x functions in terms of their respective time are written here, deterministic functions, delta dA dB. Okay. Now again, just like here, we can bring the e on the inside, which we do right here. Okay, this is the same term. We just brought the e on the inside function. It's going to be e times the product of these two x's, and then all that times the product of these two h functions, d alpha, d beta. Okay, as you can see right here, this term right here is basically our autocorrelation in terms of x. All right, I mean by definition, this is basically a definition of our autocorrelation in terms of x. All right, and our two time variables instead of t1, t2, as we define up here, are going to be alpha and beta. So this basically equates to this right here, which, because if this term right here by definition equates to the autocorrelation in terms of x, then what we're going to end up doing in the next term, as you see here, we can actually substitute in the delta. This is going to basically be delta times alpha minus beta, which we do right here. All the other terms basically stay the same. So we can say here, all right, we have the double integral of basically delta alpha minus beta, the product of the two deterministic functions, d alpha, d beta. Now, how does this break down? Well, we basically can break it down as follows. We basically choose how we want to actually arrange this sort of thing, but let's see here. So this is only going to be the only time that this function is going to be this deterministic function h of b is going to exist given this delta is when b is equal, when beta is equal to alpha, right? Because it's going to be, this term right here is going to be 0 at every point except when beta is equal to alpha, then this is going to be 0, then this inner term is going to be 0. That's the only time that the delta function is defined. It's going to be defined as a value of 1. So basically, if we actually take that in consideration, the only time this is defined is basically at h alpha. If that's the only time that is defined, then we can actually cross negative infinity to positive infinity. We can usually bring these two functions on the outside. It's going to be basically h at alpha times h of alpha, which we put right here. We rearrange the actual integration terms. We put one on the outside right here in terms of we wrote that a little wrong. Well, it's all right. So delta alpha, and then we can actually bring in the inner term right here. So this is going to be the integration across the delta function right here in delta b. This function right here, again, this is if we're going across all the possible b's. The only b, as we said, that's going to be defined at is going to be at alpha. All right. What's the value? What's the integral from negative infinity to positive infinity of any delta function? It's just going to be equal to 1. So this term right here is just equal to 1. So what we end up with is basically the integration from negative infinity to positive infinity of the square of the deterministic function in terms of alpha, d alpha. Equivalently, I mean, we just treated alpha here. We could have also just rewritten this in terms of beta, like basically the only time that alpha is going to be defined is when it's equal to beta. That would make this term like h at beta. So we could have rewritten this in terms, it doesn't really matter if we write alpha for the right here or beta. It's going to be the same sort of answer. So basically that's our answer for problem number 5 of homework number 9.